Today we are working with systems of differential equations. So let's start with this system of differential equations. Note that we have three equations here and we can rewrite it in a matricial form. So let's rewrite it in that way. Okay, here we will have the first column. Okay. Then we would have the coefficient matrix. Here today we are going to use the eigenvalue and eigenvector method in order to solve this system. So I'm assuming that you know the basics of eigenvalues and eigenvectors, okay? And also of matricial systems. So we know that we can rewrite this system of differential equations in this matricial form. So let's call this the x vector prime, because these are the first derivatives. Then here A, the matrix of coefficients, and here the x vector, okay? So let's assume here that the solution of this system can be exponential form solution. So let's assume that x is just a vector, okay, times the exponential function, okay, and t is here as the time variable. So okay, now the first derivative of this possible solution would be just the vector times, because this vector does not depend on lambda, okay, so or lambda or t, lambda t, okay. So we have these two things that we are assuming here, okay, as possible solutions. So now we can rewrite this matricial system, okay. So from here we know that this would be just, I mean, in order to understand it better, okay, here we are working with, okay, so we have this e lambda t, okay, and now yes, times ve. So as I said, these terms cancel out each other, and therefore here we have v lambda equals av, and therefore we can rewrite this as okay, this is the identity matrix, okay. Nice. So from here, if you know a little bit of eigenvalues and eigenvectors, you know that computing the determinant and equaling to 0, we can obtain the eigenvalues of this system, okay. So let's compute the determinant, okay, of this thing, okay. So we are going to do now this determinant equal to 0. So a is just this, so let's put 9 minus lambda, okay. So lambda are going to appear only in the diagonal because of the identity matrix. So minus 1 minus lambda, 0, 6, 4, 3 minus lambda, determinant, we equal it to 0. Now let's compute the determinant. This is 9 minus lambda, minus 1 minus lambda, 3 minus lambda, then we have plus 24 because of this term, okay, plus 24, 3 minus lambda. All the other terms are 0. So let's put equal to 0 and let's compute this. So we have from this term minus 9 lambda plus lambda square. Okay, this is this plus, well, let's put 24. This is yeah, 22, and therefore 24 lambda equal to 0. Let's compute this also. So this is 27 plus 9 lambda minus 27 lambda plus 9 lambda to square plus 3 lambda minus lambda to square plus 3 lambda to square minus lambda third, and okay, therefore now we can rewrite this as this is minus lambda third. Now the square is 9 plus 3 12 minus 1 11, so plus 11 lambda to square, and then here we have 9 lambda minus 27 lambda, so plus 3 we have 15, and then 24 and 15 we have 39. Okay, so 39 lambda, and afterwards we have 27 plus 72, which is just plus 45 equal to 0. We can we want to factorize this in order to obtain the eigenvalues. We can use the Ruffini method. Okay, I guess that everyone knows this method. It's pretty simple. Minus 1 plus 11 minus 39 44. Okay, this. Okay, and let's put the 3 minus 1 3 8 plus 24. This, therefore we have minus 15 minus 45 0. The next level we need 0 here, and therefore we can put another 3 minus 1 minus 3 5. This is plus 15, this is 0. And the last one is just 5 minus 1 minus 5 0. Therefore from here we have this eigenvalue. Okay, we can rewrite this as lambda minus 3 square, because we have two terms here, and lambda minus 5 equaling 0. So the eigenvalues are lambda 1 3 with multiplicity, okay, 2, and lambda 2 5 with multiplicity 1. Okay, here we have the multiplicity. Okay, so with these eigenvalues now we want to obtain the eigenvectors. So let's take this. Okay, putting this here, and now okay, we have, as we said, 5. Okay, so now let's take, we know from here, from the equation that we obtained before, that we have this. These V's are the eigenvectors, so let's obtain them with these lambdas. So let's, the first case, okay, with lambda 1 will be just 9 minus 3, okay, 4 0 minus 6 minus 1 minus 3 0 6 4 3 minus 3. This will be just, let's call this a1 a2 a3. okay, and the 0 vector, okay, because this is the 0 vector, this is the v, and this is yeah, this term here, okay. So from here we have 6, 4, 0, minus 6, minus 4, 0, 6, 4, 0. Okay, these two are the same, okay, so we can just delete one, and from here we have 6a1 plus 4a2 is just equal to 0, and 6 minus 6a1 minus 4a2 is equal to 0. I mean, this is also the same but multiplied with minus 1, so we will obtain from here, okay, we will obtain the same result. So we will have just a1 is just minus 2/3 a2, okay, and this will be just the same, and therefore the eigenvector here will be given by minus 2/3 a2 a2 a3. Okay, so let's assume now the following two cases. Okay, so we have, for example, a3 is 0 and a2 is just 1. No, let's put better in order to simplify it. This is 3, and therefore v1 will be minus 2, 3, 0, and the second option just to put this 1 and this just 3, 0, so another eigenvector from here will be just 0, 0, 1. So we have two eigenvectors for an eigenvalue 3 with multiplicity 2, so perfect, we have 2, we don't have any kind of problem here. Now let's go to the second case, okay, the second eigenvalue here. So from here the matrix is given by 9 minus 5, okay, it's just 4, 4, 0, minus 6, here we have minus 6, minus 1, minus 5, and this 6, 4, minus 2, so this is the same procedure here, 0 vector, therefore from here we obtain this will be 0 vector, is just the same thing here, the same procedure, the same method, and from here we obtain a1 plus 4a2 is equal to 0. From here we just obtain the same result, which is just a2 is minus a1, and from the last one 6a1 plus 4a2 minus 3a3 0, we can obtain, substituting this thing here, 6a1 minus 4a1 minus 2a3 equal to 0, and therefore we have a1 is equal to a3. Okay, so we have two results. So we have one eigenvector, okay, the last one, which is given by a1 minus a1, a1. Okay, and therefore we can put this as 1 minus 1, 1. Okay, so we have this we have these three eigenvalues, okay, minus 2, 3, 0, 0, 0, 1, and the third one, which is just 1 minus 1, 1. And therefore now the general solution of the system is given by a linear combination of these three solutions, and therefore x, the general solution, is given by the constant times the first solution. Okay, so let's put it like this: times the first eigenvalue plus C2 times the second eigenvector. This eigenvector has the same eigenvalue, which is equal to 3, and the last constant with the last eigenvector with the last eigenvalue in the exponential function. Okay, so this is the general result of our system of differential equation. Thanks.